Okay. All right, door is closed. Good afternoon, San Francisco. I realize that I'm standing here between you and the startup happy hour. So first of all, I want to thank you all for being here with me on this journey of building a future-proof, low-latency data system. And our focus today will be openness and interoperability. My name is Christina Taylor. I am the senior staff engineer for Catalyst Software. And what is Catalyst? We are the CDP for hundreds of customers. So the idea is infinitely nested custom objects in, relational rows and columns out. So think about your SaaS application, Salesforce, your product usage, your ticketing system, and we build an on-demand query platform that allows the customer success team to drag and drop and perform on-demand analytics. You will hear from my CEO tomorrow and the day after at the Fivetran and Databricks panel. And as for myself, you will see my face a few more times throughout this conference, whether it would be at Women in Data and AI or generative AI and bias its discussions. So instead of telling you a little bit about myself, I'd like to begin this session with some data warehouse trivia. I've got my favorite query here. Select star from big table, limit 10, right? I'm just looking around. And question here is, which enterprise data warehouse will perform a full table scan to return 10 rows? And any guesses? Last I checked, ChatGPT doesn't know this yet, so I challenge it again. I'll return to this question a little bit later in the talk, but some subject for you to think through. Okay, so today's agenda, I started with the trivia questions. I want to continue with a little bit of motivation on how we got to this multi-cloud reality and why does that matter. And I will share with you some lessons I have learned on this quest to open source and open format. I'll give you some examples, both from an architectural and actual code perspective, on how you could implement this, some incremental techniques. I want to discuss some best practices in using both fully open sourced as well as managed technologies. And I will close by some CI/CD and infrastructure as code best practices, because I believe this is the only way that your teams can work faster and scale to multiple environments and clouds. So let's set the stage here. So I have on deck a series of my employers, teams, and past employers from all different sizes, industries, and technology. So as I grow and I gain in the circle of influence, so what I've come to realize today is this. So most enterprises today are multi-cloud. And there's hundreds of different reasons why we ended up where we are today. So you might have gone with, you might have been looking for the most amount of skills, so the most robust enterprise support. So you're probably on the dominant cloud. You might have looked for the most advanced TPUs, so you wanted the best-in-class container service, then your team might be on GCP. Or you have a very strong and robust Microsoft suite, or you have something that you love and hate, but you just cannot replace. And what is that? ADF. Or, okay, so your organization might have embraced a distributed data mesh, right? That's what all the cool people are doing. Okay, so for one reason or another, most enterprises today are multi-cloud. And if you don't believe me, please read this paper called The Sky Above the Clouds. So written by Berkeley researchers and Ali Hissanbay herself. So hopefully you'll be inspired as much as I was. Anyway, again, why does that matter? So let's rewind to early 2022. So the good old times when money wasn't a problem until, well, it suddenly became a problem. And this interdisciplinary area called Cloud FinOps so rose to prominence. It is the idea of bringing financial accountability to cloud spending. So I'm going to give you a very gentle introduction here and some really basic principles. Here's a real-life example. My grandma, she was a grandmother of 5. So 3 children, 2 adopted children. And so imagining like doing planning and budgeting for such a huge family, no easy task, right? So February was always her favorite month. And you know why? And apply that principle to cloud spending. Divide the number of days in March by the number of days in February. Oops, oh, I got 10% of spending savings, or 10% more, depending on your perspective. So, right? So the point I'm making here is cloud billing is complicated. And your monthly and weekly level of detail is no longer sufficient. Hell, your cloud service provider bills you down to the seconds or milliseconds. You probably want to get ahead of your trends before the end of the month, before it is too late. Again, so what is talk without a real-life example, right? So I'm going to show you some code that ended up breaking the bank. So very simple, very innocent. I worked on a GCP team, and we needed to ship some data to the AWS team for consumption. So here is some, okay, so read from a BigQuery table and write it to AWS. So first of all, there's a little problem with this code. And can someone spot like what might be wrong with this query here? I'll take a hint. So legacy code that's got migrated from one workspace to another. So the engineer who is no longer with the company forgot to put quote around the dates. So resulting a full table scan here. Every night, this job gets run. So, but this is a limitation of the Spark BigQuery provider. So this was failing silently. So until my manager rose the question, hey, why are we spending so much taking data out of BigQuery? So how much data are we shipping? So I went to check in the Spark UI. There's like a fine line in the Spark query plan. Push all filters, null. So this date filter actually wasn't working. So every day, we ended up taking the entirety of data from one cloud into another. And I was like, oh, wow. So, OK, open source project. I go to the Spark BigQuery provider's GitHub page. I complain. I talk to our GCP account rep. What is this? OK, I don't want to go into this conspiracy theories here, but my money back. But the point is, so for every night that we're taking data from one cloud into another, cumulatively, we're spending about $200K per year. You could literally hire a full-time person, get him like medallion status on any airlines, just fly him with a hard disk from US Central 1 to US West 2, where our data centers are located. Back and forth, you would still have not spent this much amount of money. OK, so here's some perspective here. You could hire somebody full-time to do this. Now, this is what I've come to learn. Going back to the cloud billing is complicated and unpredictable problem. So there are hundreds of thousands of SKUs. So when you extract data from BigQuery into AWS, there are actually 3 major components to that bill. So the first one is select star from big table. So that's called analysis on your bill. And egress, that's the networking charges from like one region to another, one cloud to another. So in your bill, you're going to see egress to North America. But what we're really paying, because it's a cross-cloud, is the equivalent of shipping any data from anywhere in the US to anywhere in the world, exclude Oceania and Asia. So your bill says egress to North America, but if you look at actual pricing charts, we're paying a global rate because we're not only going across regions, but also clouds. OK, so the last one is going to be called streaming read. You might think, oh, I'm taking data out once a night. Like, why is that a streaming read? Well, if you use the Spark BigQuery API, that's the streaming read API call. So you are charged at the streaming read rate. So I'm not going to go into the nitty-gritty as to what exactly the numbers are. But here, the size of the pie roughly corresponds to the amount of money. So again, this thing is complicated. It's like going to the doctor in America. Like, why do I not know how much I'm gonna be charged before you touch me? And what is this, all this billing procedure codes? I need a separate degree to understand this. And I cannot use this joke with my Canadian colleagues because they live in a civilized country where healthcare is a basic human right. So they don't get it. But the point I'm making here, I hope this is going to be your takeaway, is we need accountability into cloud spending, and your monthly level can be insufficient, and the skill level details are very, it's complicated. So this is the kind of bumpy road that led me and my team onto this quest for open format and open source. So we really needed a way to avoid the costly data extraction from a proprietary, like closed format data warehouse into some open ecosystem. And we want to minimize egress between the regions and the clouds to the best of our ability. And I want to sum up the challenges we had encountered before. So again, we're using BigQuery as a destination before. So then for data transformations, we're pretty much limited to SQL or what DML the data warehouse supports. And a lot of the legacy infrastructure was put together with ClickOps. So that made it very difficult to scale. And I hope I don't have to drill in everybody's head how data export can be forbiddingly expensive. Now, you may want to ask me, what is the alternative? So if you were with me here last year, I presented this to you. So your true eventing system, a schema registry, open format, open source technology. And I was challenged in that, okay, so we may not work for a startup. We may not have access to upstream data producers or their data architects for us to implement something like this system. That's okay. And I think there are still alternatives you could work with within your existing stack. So for example, so if the below does not work for you, there are other messaging systems. So within the Google Cloud platform itself, for instance, so there's PubSub and PubSub Lite for some more real-time use cases. Or if you can tolerate, say, a 5-minute latency, you could, matter of fact, ship your data into cloud storage. So at least the data can sit in open format and using cheap storage. And if you really want to go fancy, and there is a way to union a streaming data messaging system as well as a data lake, provided that you have some centralized schema control. So you can use cheaper and longer-term cloud storage to bootstrap your real-time streaming system, i.e. the messaging system. Plus, having it in cloud storage would also ensure that you have infinite retention. So at the end of the day, what we ended up implementing was actually like a hybrid of these systems. And really, the key for us here is so that we can choose an open format and cheaper storage. And if we must take data across the cloud, at least A, we could use already what is in open format, or B, we can switch to some lighter weight messaging systems for that egress. Okay, very cool. So let's move on to the considerations for designing the pipeline, now that we have the formatting sorted out. So Spark Structured Streaming. So to be fair, Spark is not the only framework that offers a unified batch versus streaming API. But when you're choosing technology, I like to consider two different factors. So on the one hand, enterprise readiness. So on the other hand, like coolness, something like developers want to work on. And this may be different for different teams and different organizations. And for us, Apache Spark kind of strikes the perfect balance here. So it is quite robust, strong community support, open source in nature, while at the same time, there are enough developers who are very excited to work with big data technology. So again, Spark isn't the only one, but it's the one that we chose based on our organizational considerations. And these are the questions I also want you to think about when you build any pipeline. So we discussed the source and the format of data. And then, is it batch or streaming in nature? So how do you accommodate for both use cases? How do you write one version of the code that works for both? And last, perhaps the most important point I want to make with data streaming, what I mean here, not necessarily 24/7, okay, you've got a cluster on all the time, or whatnot. What I really mean by streaming and why I think this is so awesome is that it can do incremental ingestion. Therefore, you avoid the reprocessing of all the historical data. You avoid the expensive full table scans or create or replace table as select. Okay, now how do we do this? So let me skip this one and share some real-life code examples, some incremental ingestion techniques. So the first one is called streaming deduplication. So instead of calling df distinct on a large data frame, so if you know that your duplicated data will more or less arrive next to each other, what you could do is a technique called watermark. And I won't go to specific details over here. I just want to let you know that there is a way to incrementally deal with duplicates instead of having to run df distinct all the time, every time you recompute this data frame. So that is streaming deduplication. And the next one I wanted to share is incremental aggregation. So quite often you need to compute some sort of rolling average. So you could apply a window function and then continuously append this data and just recalculate when the window closes. Now there's a little bit of an art in you want to choose the threshold of your watermark and your window, and this, you know your data the best. So the short answer is the bigger your watermark, the longer your window, the most state Spark would have to track, and the most information it would need to keep in memory. Once you close the window or you progress until the next watermark, you can free up that piece of compute. But just keep in mind that your watermark and window should be wide enough to accommodate your late or duplicated data, but not so wide as to drag down the entire compute. So cannot talk about streaming on the Databricks platform without honorable mention to the golden child, Delta Live tables. So last year, I stood here to give you a developer's perspective, and today I wanted to share a little bit of insights and learning as the team lead. So some of the problems that DLT has helped us, or it may help you, is to develop quickly. So before DLT, I used to write this code in Scala. So the equivalent of light changes, let me see if I can show it to you on a repository, but it's like a significant blob of code. It's not letting me share double the screen, but I put it as a link here. So let me count here. 25 lines of code in Scala. Well, in apply changes, that's 5 lines of code. So pretty good. Well, to be honest, I learned Scala to work with Spark. You know how I feel. Scala is the way. But okay, when I have the option of writing 5 lines of code instead of 25, maybe I can save some time doing other things. So it is a very fast way to do change data capture. And it has built-in quality checks, so you can know your data failed expectations in near real time. And the data lineage, it tells you how the different tables in each step of the pipelines are related to each other. So that's one of my favorite features. So if I want to debug something, like my data is wrong, so that's how I can track them down upstream in the data workflows. And the last one, and I kind of hate this democratization buzzword now, but the perspective I got was actually this is a great tool for someone who coming from a data science and analytics background, getting an entry into the world of PySpark. So for them to move a little bit beyond their analytics career into data engineering. So in my last team, we actually had data scientists making commits to a Delta Live Tables pipeline. So it worked out pretty sweetly with my team. Now, what should we be mindful of? Disclaimer, I got this before the Hollywood writers went on strike. This was a last week tonight episode. I don't know if you like Slim Jims, but I do. So I chew on them when I think, okay, I need a way to automatically discover and register all my tables in a catalog. So I wrote a script that does that programmatically and recursively. And I say, the command prompt it took, by the way, is, hey, Dolly, can you help me discover all my tables? It's actually just Boto and DBFS under the hood. But what I don't want this to happen for you, like I'm using any managed systems, like DLT or not, is this. So what should we be mindful of? So this is something that I firmly believe. So cooperation between agents, algorithms, and humans depends on trust. So if I were to accept any managed systems prescriptions, I must understand and I must be able to trust them. So did you read the fine print? There are actually a lot of configuration options when it comes to DLT. So for example, CDC properties. So it controls things like how much your data can be out of order. So it controls things like how often are tombstone records inserted and deleted. Does that work for your data? And one of the things that DLT does automatically is it runs optimize and table maintenance every 24 hours. But to do that, you need to properly configure a maintenance cluster with the correct IAM roles that has access to your data. And we've hit some landmines here in that we specified specific cluster settings. And by default, that got applied to both the maintenance cluster as well as the job cluster. But that specific piece of configuration does not work with the default maintenance cluster, which is a C-type compute optimized AWS instance. So you can change all of these things, by the way. So this is a highly customizable framework, but you need to be aware that these fine prints and options do exist. So, and there are other things like pipeline properties. So by default, a flow will retry twice when it comes to a recoverable error, and a job, a pipeline will retry 5 times. Is that the behavior you want? Do you need it to be retried more or less? So, and then the last one is apply change options. So there are all these parameters called ignore nulls, include or exclude columns. Why are they there? So what can you use it for? Read the fine print. I'll tell you what we use ignores for. Ignore nulls. Occasionally, because we use dbZim for change data capture, so occasionally we get like for simplicity's sake, like garbage data, it's called toast value. You can look up, there's like an entire blog on what produces toast values upstream. But we don't want to ignore that column. We just want to ignore that particular value. So in DBZim configuration, I can actually set my representation of garbage data. So instead of toast value, I can choose that to be null, and I can tell DLT to ignore nulls instead of having to re-engineer a whole data cleansing pipeline. So it's pretty sweet, but read the fine print. All right, so let's move on to something that I personally feel very strongly about. So I'm not a DevOps manager, I'm not SRE, but maybe I was in my past life, because I believe the ability to manage your infrastructure and workflows in code is the only way that your teams can scale to multiple environments and clouds. So think about it. And here are a few options I'm presenting to you. So the first one is an open source Databricks Labs project called the DDX Project. And it integrates very well with GitHub Actions. Here is an example workflow. So on committing to your main branch or tagging a specific release, so the DDX project can run within Actions, a repo sync, and a deploy. And all of that are managed by configuration files in YAML format. So in other words, you would just need to set up GitHub Actions and write some YAML files for you to be able to set up your jobs and dependencies and scale to multiple environments and clouds. And let's take a look at how one of these YAML files look like. And this is one of my favorite features about the DDX project. So you can use a technique called EML Concatenation. So there's no magic here. So everything that works with PyYAML works with the DDX project. You can chain your permissions, your cluster settings. You can chain Delta Lab tables and just regular Databricks jobs. You just need to specify which job depends on each other. And this uses the Databricks jobs API at the backend. So whatever parameters jobs API supports, and the DDX projects usually support it. And again, open source project, you can contribute to. I've given the project some of my feedback as well. To sum up, the advantages, it's very easy to configure, and it's very easy to set up. It's just a Python library. A data scientist can do it. And it offers an out-of-the-box Python packaging solution. So you don't have to write your setup py files. So this will generate a requirements.txt and a template for you. So super easy to use. There's like handy commands such as DDX sync, DDX launch for you to run interactive workflows. And you just need a Databricks API and token. So extremely straightforward. Now, some criticisms are going to be related to the strength. So the DDX project uses MLflow experiments as the backend, and it relies on the MLflow uploader. So it generates a random SHA where the Python package is stored, and some people doesn't like it. And the other one was more opinionated. Some people hate Python packages. Other people have opinions about using YAML as your configuration language. So these are all valid concerns. So may I introduce to you like a second option? So there is the Databricks Terraform provider. Again, you could easily integrate it with GitHub Actions, Circle CI, Jenkins, whatever your CI/CD tool is. This is an example of using the Terraform project with release branches, so you can develop independently. And for those who need a gentle reminder on how Terraform works, it is just using infrastructure as code to bring your infrastructure from current state to ideal state, whatever you specified in the Terraform configuration file. So there are 3 steps here: init, plan, apply. So init installs the necessary modules. Plan draws up the blueprint how to get from A to B. apply these changes to get your infrastructure to match your configuration. Okay, so I can show you some of my favorite features again about the Terraform provider. I find it works very well with Git source and branches. So when I was developing, I often wanted to run a local Terraform plan and apply. So I want to point it to my personal branch. And in a real-life scenario, what you might want to do is this. So on merge to staging, run the Terraform apply against your staging environment. On the merge to a feature branch, run the plan and apply against that feature branch. And all of these can be independent. And this doesn't rely on the Databricks repo object at all either. So there's no danger of someone just, clicked into the UI, into the notebook, made modifications, but didn't commit back to Git. Okay, some strength of the Terraform project is Terraform not only manages your job, it can be used to manage all of your Databricks infrastructure. I actually do this with Databricks Unity catalog. It's a lot of pain and a lot of fun. I told you that I learned Scala to work with Spark. I learned Terraform to work with Unity catalog and Databricks workflows. But anyway, so it is cloud and CLI agnostic. I like that it works very well with Git branches, and it doesn't rely on MLflow experiment. But some caveats here. So you will still need a separate Python packaging solution. The DDX project will package your wheel for you. Terraform will not. And quite often, it requires some pretty sophisticated IAM permissions for you to apply this, because probably in most of our cases, it does talk to cloud resources. And a catalyst, so the Terraform state lives in GCP, and the infrastructure, the Databricks stuff we want to apply, it's in AWS. So I needed some DevOps support in making that work, and it does have a steeper learning curve. So it may be a lot to ask your data science and data analytics team to get on board with this, but if you have a strong and hungry engineering organization, I really do recommend this, because guess what? It's a really good developer to learn and for engineers to gain their skills. So what I wanted to stress over here is I want to go beyond what is just notebooks or SQL scripts that lives in an admin's workspace. Or is it searchable and everybody's notebooks out of the Git repository? Saved queries? No, I think in a multi-cloud and multi-environment world as of today, and that approach is really difficult to scale. So infrastructure as code, something that I feel really strongly about. All right, I think I have 5 minutes to take some questions before I close out. But here in the end of my presentation, I've linked all the resources with links that you can check out. Okay, does anyone have any questions? Sorry, what was that? So the version 1 of our stack was actually services directly into BigQuery. And we run into some challenges, not only with the extraction problem, but also there's limitations on what we can do to transform data within SQL. So version number 2 was actually the same services. We're using a data flow job. So the services give us PubSub events, but we're using a data flow job to copy from PubSub into cloud storage. So that's both for infinite retention and for easier ingestion downstream using autoloader or DLT. Because I think Spark doesn't support PubSub yet, and it does support PubSub Lite, but it's a little finicky. Again, coolness and enterprise readiness. OK, so I'm going to hang out here for 5 more minutes, but I want to close out with this. And I actually did write this, and ChatGPT did not. So the future-proof data ecosystem is open format, so you can be cloud agnostic. It is open source, so you have the flexibility and control. And at last, it is source controlled. And that is the only way it's scalable. Thank you all.